Now we're going to look at solving projectile problems and kind of some basic strategies that will help in approaching problems that, where we have to keep track of both vertical and horizontal directions at the same time. In general, these problems are not too much different from our one-dimensional problems. We just have to do two problems for each, or two calculations for each problem. We have to keep track of the vertical and the horizontal stuff. But other than making sure to get some kind of bookkeeping system to not mix the vertical information with the horizontal information, other than that, it's pretty much the same approach as we had to our one-dimensional kinematic problems. So let's start out here by looking at a couple of fairly simple situations. It's a wonderful drawing here of mine. So let's say we've got a table. Yes, this is a table. Maybe I'll put it, yeah, something like that. And we have a ball rolling on that table. While it's on the table, let's say the velocity is 5 meters per second, traveling this way. It rolls off the table. Let's say the table is 1.5 meters high. So from here to there, it's going to follow a parabolic trajectory, as we all know, splat on the ground there. And I want to know this horizontal distance here from the edge of the table to where the ball hits the ground. Alright, so for every single projectile problem, what I would suggest doing is making a nice table of data where you keep the horizontal and the vertical stuff separate. So vertically, we have accelerated motion, as we mentioned in the last video. So we have our entire list of quantities that apply to accelerated motion. I guess I need that a little longer. Okay. Now in the horizontal direction, we have constant velocity, so we don't have to distinguish between initial and final velocity, and we don't have acceleration. All we need is delta x. Oh. Okay, delta x, and then we need the velocity in the x direction. If you want to, give subscripts x's and y's or something like that on those, you can, if that helps. We also have t over here. Now, all of these things are independent. The velocities in this direction don't affect the velocities, the distances don't affect the distances, but the time is the same. If I know the time on one side, that's equal to the time on the other side. If you want to put it in the middle or something to show that it applies to both, that is fine. We're simply saying that the time it is traveling vertically is the same as the time that it's traveling horizontally. So if you want to kind of set up this table before you start every problem, that's good. As always, I'm not going to require that. I'm not going to look for that on your homework or a test or anything. But if you don't know where to start, or if you have problems putting vertical velocities over here with the x stuff, maybe you want to think of using a system like this to keep track of everything. Alright, so let's get started filling out our table here. This is always going to be true, right? So I guess before filling out anything specific to this situation, you could always start with that as well. Alright, so we have this 5 meters per second here, and that is the velocity as it's moving along the table. It's not a projectile when it's on the table. It becomes a projectile the instant it leaves the edge of the table. But what do we know about the horizontal velocity? Well, it's constant, so the velocity on the table is equal to the velocity while it's a projectile. So we know that that 5 goes over here in the horizontal velocity. What else do I have? I've got a 1.5, that's a vertical height, so I'm going to put that here. Now we need to check direction. I start up here and I end down here, so the direction of my vertical displacement is down, direction of my acceleration is down, so they can have the same sign. We might as well leave them as both positive. The initial velocity in the y direction, well, it starts gaining velocity when it leaves the table, but the very instant it leaves the table, it was just traveling horizontally. So we say that the initial velocity in the y direction is 0. Now later on we're going to see things launched at angles, and there's a couple of extra steps there, but that'll be in the next video. Your first assignment is only going to deal with situations similar to this, where you are being launched initially with just a horizontal velocity, which makes the calculations a little bit simpler. Alright, I want to find this right here. Well, that's my horizontal displacement. Sometimes you'll often see this called the range of the projectile. Okay, for fairly obvious reasons. They started being concerned with these calculations when they started shooting cannons and things like that, and they wanted to know how far of a target they could hit, and so you call that the range, is the horizontal displacement. So here's our setup. I want to find this. Now, one other thing with your initial setup, if we've got constant velocity over here, we're not going to use one of those 4 kinematic equations for constant acceleration. If we've got constant velocity over here on the x side, we are only ever going to use this one equation. That is it. That's the only equation we'll ever use for the horizontal side. On the vertical side, sometimes we will use a number of those constant acceleration equations, but probably like 95% of the time we end up using this equation. Okay. So I'm over here, I've got the 5 I could plug into my equation here. I'm trying to find delta x, that's what I'm looking for, but I don't have the t. And I can't find t if I don't know x either, so I'm kind of stuck. But as this arrow indicates, hey look, if I can find t over here, that tells me the horizontal t as well, and then we'll be in business. So we'll go over here for now, and I can start plugging in my numbers. I've got a displacement of 1.5, initial velocity 0, half of my acceleration is 4.9, t squared. So I'm going to have t equals the square root of 1.5 over 4. So if you're one of those mental math geniuses, go ahead and do that in your head, but I will grab a calculator and I get 0.553 seconds. Okay, that's a rounded answer, obviously. But now I can take that 0.553 and put it in both places, actually, if you'd like. But now I have the time to plug into this equation over here, 0.553. Since this is a rounded answer, be careful. I just have the number in my calculator, so I'm taking all the digits my calculator can keep and multiplying by 5. If you're not able to do that because your calculator can't do that or something, I would probably keep a couple more digits here, 4 or 5 digits at least. Okay, so we multiply those two guys and we get 2.766, so I'll round that to 2.77 meters. I want to make that approximate. Okay, so there is our answer. That is how far from the edge it will land. Simple enough, yeah? Alright, let's look at one other example, pretty similar situation, but where we're given slightly different information. Let's make it a cannon up on a cliff. There's our wonderful cannon, there's its fuse. And this cannon, even though it doesn't look like it, we're going to say it's pointed directly horizontally. So this ball is flying out at, cannons are going to be faster, let's say like, let's go faster than 20. Let's go 40 meters per second. Directly horizontally. Okay. Let's say we still know how high the cliff is. No, we can't know the height of the cliff. Oh, hold on. So this time, let's say instead of knowing how high the cliff is and figuring out how far it went, let's say that we go and measure how far it goes, and we find, let's say 120 meters horizontally. And now we are going to find how tall was that cliff. Actually, it's not the cliff exactly, but where the cannon is what was the height that the ball was shot from, right? Okay, so we start with our wonderful table of vertical and horizontal information. You've got delta x, v, and t over there, delta y, v naught, v, a, and t over here. Okay. We are assuming this is launched directly horizontally. The piece of information that gives us is that our initial vertical velocity is 0. This here is what we're trying to find. We don't really care about that. Acceleration is 9.8, and this time we're given the horizontal displacement as well as the horizontal velocity. So if I want to find this, I need to know one of these two things. I have no way of finding this directly to begin with, but I can find t over here and use it over there. So using the only equation I ever use for the horizontal motion of a projectile, we get 120 equals 40t, so t equals 120 over 40, so we get that our projectile was in the air for exactly 3 seconds. Come in and plug that in over here, and then we want to find delta y, the equation we use almost all of the time in the vertical direction. Delta y equals v naught t plus 1/2 at squared. This guy is 0, so all we have to do is worry about this 1/2 at squared, so that's 4.9 times 3 squared, or 4.9 times 9, which my calculator tells me is 44.1 meters high. Okay, so that's our vertical height from which our cannonball was launched. So your first assignment is going to be a series of problems, all pretty similar to this. If you want to you can just jump right in and solve it, great. If not, try to find a way to organize your information and have a strategy like this. All right.